Okay, so far, let's review real quickly what we've done last time with the different gas laws. We had Dalton's law of partial pressures that basically says that if you add up all the partial pressures of gas in a container, that will equal the total pressure. And really what it means, doesn't matter what the gas is, it really just matters how much gas is in the container. So if you had a mole of oxygen and a mole of hydrogen in a container, you have the exact same number of particles of both. And let's say the container had a total pressure of 1 atmosphere, their partial pressures would each be 0.5, would be half of the total. And so that's Dalton's law of partial pressure. Then we talked about Boyle's law, pressure-volume relationship. If you increase the pressure on a gas, then the volume will decrease. And so those are inversely related. Charles' law, the relationship between volume and temperature. Again, if you have something like a balloon that could actually expand, if you increase the temperature, the molecules start moving faster, hit the walls of the container harder, and it starts to get larger. So in that case, temperature and volume are directly proportional. That's Charles' law. And remember, all temperatures have to be in Kelvin when you're doing gas laws. And then Gay-Lussac's law was the relationship between temperature and pressure. Let's say, again, you have an aerosol can, you throw it in a fire, the temperature of the molecules, they start moving faster and faster. They start hitting the walls of the container harder, and therefore the pressure goes up. And so, again, that's a direct relationship between temperature and pressure. So now we're looking at, is there a relationship between pressure, temperature, volume, and the amount of gas? And really, this is called the ideal gas law that relates all of them. And you use it, for instance, what we've been, and when we talk, when we solve for volume in chemistry, what we do is we'll go, okay, if you have 2 moles of something, how many liters would it occupy? And a mole of anything occupies 22.4 liters, but that's at STP, standard temperature and pressure. Standard temperature, though, for these kind of measurements is 0 degrees Celsius, which is 273 Kelvin. And then standard pressure would be normal conditions anywhere, like 1 atmosphere, 760 millimeters of mercury, or 101.3 kilopascals. And so if I said, though, what would a mole of gas occupy right now? Well, it's not standard conditions. It's not 0 degrees in this room. The pressure is probably close to 1 atmosphere, but not quite. So, because you have to understand that pressure and temperature will affect the volume of a gas. So this is the law we use when if we said, what does the mole of gas occupy right now, we would use the ideal gas law, PV equals nRT. Again, P is pressure, and that would be in units of millimeters of mercury, atmospheres, or kilopascals. Volume must be in either liters or decimeters cubed, but if you remember from the beginning of the year, a liter is the same thing as a decimeter cube. We use one for regular shaped objects and one for typically liquids or irregular shaped objects. N is moles, so N is moles. And T is temperature. Remember, it's temperature, it must be in Kelvin. And R is the universal gas constant that relates all of them. And I'm going to show you real quick how they end up with R. And it'll actually, since pressure can be in millimeters mercury, atmospheres, or kilopascals, that's the only one that could be in different units. R, the universal gas constant, will depend on the pressure unit. So let me show you real quick how they get that and why it changes depending on pressure units. If you rearrange this equation to solve for R, PV over NT equals R, and you plug in all standard conditions for a gas, multiply, cross, and divide, you'll get R. What do I mean by that? Well, let's say a gas is at 1 standard atmosphere pressure. The volume, remember, of a mole of any gas would be 22.4, and that would be 1 mole of gas. Standard temperature is 273 Kelvin. If you multiply across, then divide, you'll get 0.0821 for R. And again, that just relates all of those variables. But remember, if we change this then and said, okay, well, what if we say, though, the pressure is in 760 millimeters of mercury, then suddenly that changes R. Again, multiply, cross, and divide, you get 62.4. So that's where R is derived from. You're not going to have to do that. I'm just telling you where it came from. So here again, you don't have to memorize these, obviously. They're going to be in your notes for you. But you do need to remember, because when you go, well, what do you mean these are constants, yet there's 3 of them? It depends on what the pressure is. That will determine what R you actually use when you're solving problems related to that. And again, if you're wondering, well, how are you going to know when you mix all these equations up when to use ideal gas law? It is the law that relates pressure, volume, temperature, and the amount of gas. So when you're looking at these problems here at the bottom, we've got 20 liters of gas at a pressure, 2 times 10 to the 4th kilopascals, 28 degrees Celsius. How many moles? Again, this is the only law that is going to relate all of those things. And so you plug all of those numbers in and then solve for x. So again, the pressure is 2.000 times 10 to the 4th kilopascals. And the volume is 20 liters. And remember, the volume does have to be in either liters or decimeters cubed. So if they gave you something in milliliters, you're going to have to convert it before you put it in the problem. And N is always moles, and if they give you like grams, you're going to have to convert that before you put it in the problem. So in this case, they're saying how many moles. That's X. Remember, R is determined by whatever the pressure is in kilopascals. You go back up here. If pressure is in kilopascals, R is 8.31. Again, it's the universal gas constant. Temperature must be in Kelvin. 273 plus 28, again, is 301. So solve for X. So multiply those two numbers together and divide by 8.31 and 301, and X ends up being 160 moles of N2. And if they asked that question, well, how many grams of that gas would you have? You could then take that and multiply it by the molar mass of nitrogen because it's diatomic. And so there you go. I used I put a decimal there because we need 3 sig figs in the answer there. And that's the only way to count that zero is to put a decimal after, because remember the rule for sig figs or zeros is trailing zeros count when there's a decimal somewhere in the problem. All right, next question. 2.24 liters, or 2.24 times 10 to the 6 liters of methane gas. We've got pressure. We have temperature. How many kilograms are in there? Now remember, kilograms is not in this problem, but you need to understand anytime you have moles of something, you can convert it to grams. And in this case, we could convert it to kilograms as well. So plug everything into the equation, and then when you get moles, convert that to grams and then convert it to kilograms. So let's plug everything in. 1.50 times 10 to the 3rd kilopascals. And the volume, 2.24 times 10 to the 6 liters. And again, they're asking for kilograms. We're going to go to moles. That's what we can get. That's what N is. Universal gas constant, again, is determined by the fact that pressure is in kilopascals. So again, it's 8.31. And temperature is 42 plus 273, or 315 Kelvin. Multiply across and solve for X. You end up X, or multiply across, then divide, obviously. So you get, X is 1.28 times 10 to the 6 moles of CH4. But now we can always convert that to grams. So if they're asking for grams, in this case they're asking for kilograms, we can do that as well. So we can go to grams of CH4 over moles of CH4. Don't forget that we've been converting like this all year. How do we know what that weighs? Carbon weighs 12, and hydrogen weighs 1 apiece. That's a total of 16 there. But again, we want the answer in kilograms. So we want kilograms of CH4 over grams of CH4. And again, it doesn't matter what you put in conversion factor, they must be equal. In this case, we have kilograms to grams. You need to put a 1 in front of whatever's largest. 1 kilogram is 1,000 grams. Again, if you don't know that, you should just be able to look that up. So 1.286 times 10 to the 6 times 16 divided by 1,000 to get our answer there. And we end up with X is 2.05 times 10 to the 4 kilograms of CH4. All right, moving on to the last one. There's a couple more problems on the next page, but I'm saving those for later when we do gas stoichiometry. So the last one for today. Again, it says what volume. So volume is what we're looking for. We get 12 grams of oxygen, 25 degrees Celsius, and we have pressure as well. Well, 12 grams, we cannot plug that into that equation, but again, you have to remember we can convert that to moles real quick and then plug that in and use PV equals nRT to solve that problem. So first thing you got to do is take your 12.0 grams of O2. Remember, it's diatomic, so it's O2. We're going to convert that to moles of O2 over grams of O2. 1 mole weighs 32 grams, so 12 divided by 32, that is 0.375 moles of O2, and now we can solve the problem. And so they're giving us a pressure of 52.7 kilopascals. Volume is X. N, remember we've worked that out, N is 0.375 moles. R, again, is based on kilopascals, and keep in mind all of these we had a pressure in kilopascals because that's metric units, but pressure can be in millimeters of mercury in atmosphere, and again, you're going to have to refer back up here when that's the case and use the proper universal gas constant. So again, so R, again, is 8.31. And temperature, remember, can't leave it in Celsius. All gas laws, you need the temperature to convert it to Kelvin. So 25 plus 273 is 298. So multiply, cross, and divide. X ends up being 17.6 liters. You'll have some go formative problems to work on. And again, I mix them up pretty well. So good luck with those. And next time we'll show you how to use ideal gas law to solve for molar mass and density.